Hello everyone, welcome to this second video on formation of PDE by elimination of arbitrary functions. In this video, we are going to see how to form a PDE by eliminating the arbitrary functions using determinant method. So now let us consider one example. So this is what our given example. So this is of the form f of u comma v is equal to 0. So this is taken as u and this is taken as v. So now let us name the given equation as 1, and we have only one arbitrary function involved in the given relation. So we are going to differentiate the given equation with respect to x and y. Since we have a relation which is f of u comma v is equal to 0, and differentiating this 1 with respect to x means first we have to differentiate this f with respect to u, and then we have to differentiate this u with respect to x, which is also a function of v. So here we use addition symbol. So we have to differentiate f with respect to v and v with respect to x, and in the right hand side we get 0. Similarly, differentiation of the relation with respect to y partially means we have to differentiate the function with respect to u, and then that u can be differentiated with respect to y. Plus, since it is a function of v also, so we have to differentiate this with respect to v, and then that v has to be differentiated with respect to y partially. And in the right hand side we have 0. So from this what we get, dou f by dou u, and dou u of dou x means we have to differentiate the whole function with respect to x means here differentiation of x square is 2x. Since z is also a function of x and y, differentiation of z square is 2z into dou z by dou x, which is nothing but taken as p. Now when you come to the second term, it is dou f by dou v, and dou v by dou x means we have to differentiate this v with respect to x. So in that first term is ax, that comes as a, plus here we have z also. Z is also a function of x. So differentiation of this gives c into dou z by dou x, which is nothing but c into p, which is equal to 0. Similarly, when you differentiate the function with respect to y partially, we get dou f by dou u into dou u by dou y. So now we are differentiating u partially with respect to y means first term will become 0 and this term is 2y. So it is 2y, and z is also a function of y. So this comes as 2z into dou z by dou y, which means q. And in the second term it is dou f by dou v, and differentiation of v with respect to y now, it is actually it is plus by, so it is b, plus differentiation of this cz with respect to y, it is c into dou z by dou y, which is nothing but c into q. So from this we are going to write the coefficients of the derivatives in determinant. So we are going to express the coefficients in 2 by 2 determinant form, that is 2x plus 2zp and a plus cp as the first row, and 2y plus 2zq and b plus cq as the second row. And in the right hand side we have 0. So this can be equated to 0. And solving this determinant, we get our final PDE as cx minus az into q plus bz minus cy into p is equal to ay minus bx. So we can say the resultant PDE is obtained in Lagrange's form. So what is Lagrange's form? capital P into small p plus capital Q into small q is equal to R. So this form of PDE is known as Lagrange's form of PDE. So in this case, we obtain our resultant PDE in this form. So now let's see one more example. So here we have two arbitrary functions. So now we are going to differentiate this twice. Let us name the given equation as 1. When you differentiate this 1 with respect to x and y, you get the left hand side is dou z by dou x, and in the right hand side it is f dash of 2x plus y into 2 plus g of 3x minus y into 3, because we are differentiating this with respect to, sorry, g dash of 3x minus y into 3. Now we are differentiating this with respect to y. So we get dou z by dou y in the left hand side. So this can be taken as p and this can be taken as q. So in the right hand side we get f dash of 2x plus y into 1 plus g dash of 3x minus y into minus 1. So now we are going to differentiate this again with respect to x, so that we get dou square z by dou x square, that can be taken as R, which is equal to f double dash of 2x plus y into 2, again already we have 1 2, so it comes as 4 plus g double dash of 3x minus y into 3, again already we have 1 3, so that comes as 9. So now we are going to differentiate the same with respect to y, which gives s, that is dou square z by dou x dou y, which is equal to f double dash of 2x plus y into 2 plus g double dash of 3x minus y into minus 3. So now we are differentiating this equation with respect to y, which gives t, that is dou square z by dou y square. So differentiation of this with respect to x, again we get dou square z by dou x square, that is nothing but r, and differentiation of this with respect to y, again we get t, which is nothing but t, that is dou square z by dou y square, which is equal to f double dash of 2x plus y into 1 plus g double dash of 3x minus y into minus 1 again, so that becomes plus 1. So now we are writing the last three equations in 3 by 3 determinant form. That is, how can we write the last three equations in 3 by 3 determinant form? Just keeping the coefficients of the derivatives term, means the derivatives of arbitrary functions in the determinant. How can we write it? That is, here the coefficient is 4, here it is 9, here it is 2, and here it is minus 3, here it is 1, here it is 1, and in the left hand side we have R, S and T. So now we are writing the coefficients in 3 by 3 determinant form. So it is 4, 9, R, and 2 minus 3 and S, and 1, 1 and T. So now solving this determinant, we get our resultant PDE as S plus R minus 60. X plus R minus 60 is equal to 0. That is, the resultant PD is nothing but dou square z by dou x dou y plus dou square plus dou square z by dou x square minus 6 into dou square z by dou y square is equal to 0. So this is what our resultant PDE. I hope you understand this concept. Thank you for watching.